In this lecture, we want to continue our discussion of hash tables. Essentially, hash tables have to deal with the problem of collisions, which we discussed in our last lecture. A collision occurs where two keys end up at the same array index or the same location in the data structure. And so there has to be a way of dealing with two or more elements arriving or set to be stored at the same location. So these two strategies are first probing and then chaining. Probing is also referred to as open addressing. What this means is the actual location of the element to be stored is not fixed and known, but rather can be changed. However, with chaining, we have closed addressing, which means the element is stored exactly at the place it hashes to. So I want to switch over to my sketchpad here and look at the ideas of how these two work at a little bit higher level. Alright, first I want to look at probing. And so the idea for probing is open addressing. So suppose then that we have letters that were stored here. Let's go ahead and add some. B, C, Q, F. Now suppose that I want to insert a new element in, and it hashes to this location in the array, but it can't go there because that location is already occupied. Therefore, there must be some set of rules or heuristics for relocating into an available slot. There's several of these strategies that we want to look at in a minute, the simplest being linear probing, where you shift down one to the right and see if that spot's available. No, it's not. It has a C in it. So we go down and check this one. Not available. Shift down, check this one. Not available. Scoot down, check this one. Not available. Scoot down, check this one. So then we put the N in this location rather than where it was supposed to go here. So for searching operations, if you're looking for the N, you go to the spot N hash to, which is this spot. And since the N isn't there, then you have to move down until you find it. So we have precisely 1, 2, 3, 4 shifts or 4 cells that we consider as candidates before we find the N. Well, 4 out of however many elements might be in the array or the hash table are not significant. Therefore, this operation remains big O of 1. Now then, the other alternative is chaining. So this strategy is probing. The strategy we want to consider next is chaining, and this is the one that you will generally use to implement projects in CS310. It's far more flexible, and it works better in the case where you have many insertions and deletions. And the idea is a simple one. If this is the spot where the N needs to go, then that's exactly where it does go. The idea is you create an array, but an array of linked lists. So here we have linked lists. This one is empty. This one may have, let's say, 2 elements here. So let's say X and then maybe Q. And then this one may be empty, and this one may be empty. And this one has several elements in it. B, C, Q, and so there's not room. I'm not going to write F. If we're going to insert N, then we insert it right here. The idea being then, if we're going to search for N, we go to exactly the index where the N is supposed to be, and then we call search or find operation on this linked list. So we scan down looking for the N, and then here we find it and return that node. So this is the idea of chaining then, that we have linked lists here rather than single elements. This way we can store multiple elements in one location. And again, this is big O of 1 because in the worst case, you're going to have 3 or perhaps 4 elements in a linked list. And doing 3 or 4 elements to find something in a linked list is certainly acceptable. And it's big O of 1. It's big O of 1 because the size of the linked list is not in any way related to the input size n. That is, the length of this list has nothing to do with how many elements are actually in the hash table, and therefore it is a big O of 1 operation. So these are our two strategies then that are generally used for dealing with the collision problem. Two very different implementations of the hash table data structure depending on the requirements for the project. So for probing, we want to look at that first. Where you're doing an insertion, if you go to the array element indicated and discover that it's already occupied, then there must be some heuristic to go to an alternate location. So there are a number of these. We only want really right now to look at two, the most common ones. With linear probing, you move one slot to the right until you find one that's unoccupied. That is, you may scan down 1, 2, 3, 4 or more spaces until you find a vacant slot, and when you do find it, then the element is stored there. And so when you're doing searching, you follow the same process, and you go until you either find the element or know that it could not be in the hash table. There is a problem with this strategy, though. There is a propensity for hash codes to cause clustering, which we will talk about in just a moment. Clustering is the tendency for keys to group together in the hash table. That is, you may have vast expanses of vacant slots, and then all of the occupied ones are next to each other. So quadratic probing is a way to deal with this. And so what you do is you move down, but not one slot at a time, but in a series where you move one slot down, and then 2, and then 4, and then 8, and so on, until you find a location that is vacant and available, or in the case of searching, till you find what you're looking for or find that it cannot be in the table. Quadratic probing causes these various sized jumps, and in these cases the hash table should be a prime number. This is important because if you wrap around with a number that's a power of 2, then you'll hit the same cells over and over again, but you cannot be certain that you will hit every cell in these cases. And so by having a prime number, when you wrap around from the end of the array back to index 0, you will hit a different set of cells. So again, quadratic probing is a strategy to deal with clustering. And this is the tendency for hash codes to end up in the same or close to the same spot. We hope for a perfectly even distribution of the keys, but we really never get that. And it turns out that the keys will tend to group together in certain sections of the array. Quadratic probing does break up these clusters, but secondary clustering may result as a consequence of quadratic probing. So this is an example of what clustering looks like. Here we have an array, but rather than printing array elements, what I have done is printed the number of elements that have hashed to this slot. So for instance, starting here at index 0, it's empty. Here one element goes at index 1, one at 2, one at 3, and so on. Here in this location we have 2 elements that have hashed to these spots. And so you can see the concept of clustering here. Look at the vacants. Where are the zeros? The zeros almost never occur all by themselves, but they are in groups. Here we see the zeros. They're not by themselves, they occur in groups. Similarly, the occupied cells occur in groups. Notice here at the end, this big section of zeros here, and then these with ones. This is actually quite good. The distribution of keys across this hash table is actually very, very good. But here you can clearly see the concept or the idea of clustering, how it occurs and what it means. And so here we see this vast expanse of zeros, but there are other sections that have all elements, ones, even twos. So we're trying to get a more even distribution, and quadratic probing is a way to help with that. Hash tables should always be made larger than the maximum number of entries. That is, we have different sizes we need to keep track of. One is we have the current size. That's the number of elements that are currently stored in the hash table. Two, we have the max size. This is the maximum number of elements that can be inserted in the table. Now we of course have a max size because hash tables are array-based, and the array has a finite size limit. So the max size is the maximum number of elements we're going to allow to be stored in our hash table. The third one we have is table size, and table size should always be made larger than the maximum number of elements the table will contain. About 1/3 larger is a reasonable amount. So for example, if the maximum size of the table is 100,000, then you should make the table size 130,000. And here's the standard formula for setting this. You have the max size and you multiply it by 1.3, and that will give you about 30% more. The F, by the way, here stands for float. Without it's a double. Doesn't really matter, but in general you want to put 1.3 F for float to give you a 30% larger table size. So this is done to lessen the impact of both collisions and clustering. If quadratic probing is used, then the size of the array should be a prime number so that you hit different cells if you wrap around again to index 0. So as you can see, we're guaranteeing here that we're going to waste space. If our max size is 100,000 and we have made the table of 130,000, then it follows that at least 30,000 cells will be vacant and unused. However, this is acceptable because what we're doing is we're trading off storage space for improved performance. That extra buffer, that extra space, helps when we're trying to figure out how to deal with collisions. We have minimized the impact of collisions by having extra space in the table. This leads me to the discussion of load factor lambda. The load factor is very important. It's the percentage of the table that is occupied. So if the table's half full, then the load factor is 0.5 or 50%. It's half full. This has an effect on the expected number of probes, and this should be really fairly obvious if we're considering a probing strategy. If we hash to a certain cell and that cell is occupied, then we must shift down until we find an available vacant cell. But the more full the table is, the longer this is going to take. So when we talk about probes, we mean looking for available slots. The number of probes means the number of checks or comparisons we must make to see whether or not we have found a place to store an element we want to add to the table. So there's a slight difference in the two formulas here. An unsuccessful search is somewhat worse than a successful search, because with the unsuccessful search you have to exhaust all possibilities. So here's a graph of what happens with the number of probes, or the search times, as the table becomes more and more full as the load factor lambda increases. So at this point here at 70%, so at this point the table is 70% full. From this point on, the number of probes goes up dramatically. So in the case of a 95% full table, we have 200 or so probes that are expected. That means if you're searching for an element, you're deleting an element, or you're adding an element, you may have to look at 200 locations before you find the one that's going to work. And so having 200 locations obviously is going to seriously degrade performance. Whereas if you're looking at a table that's half full, then you're looking at 2, 3, maybe 4, and no more than that. This is a striking difference in performance. So some comments here about probing. Probing is best suited to hash tables that have relatively few insertions and deletions once they're created. There are a number of problems that have exactly these characteristics. For instance, you might have a hash table that you're using for looking up prices in a retail store. When you start the computer, you load the hash table and it's all the products that this company has. And so, of course, they may stop carrying things or they may have new items that they add. However, the number of changes to the hash table is relatively minor. There are very few changes once it's initially created. This is something that changes very slowly over time. So probing is best suited to these types of problems. In the best and the average cases, probing is generally faster than chaining. Now, when we say faster, we mean wall clock or empirical times. If you run timing tests on the two implementations of hash tables, then what you will see is that probing is somewhat faster. Nevertheless, both of these implementations are big O of 1. It turns out that linked lists have overhead that slow things down. That is, with probing, once you go to the cell that contains the element you're looking for, it's right there. However, with chaining, once you get to the location that's indicated, then you have to perform add, delete, or search operations on a linked list, which may mean creating new nodes, allocating memory. It may be freeing up memory with the garbage collector. And so there's more overhead associated with using linked lists, and that causes a slightly slower performance characteristic. Performance of all hash tables degrade when the load factor increases. With probing, the degradation is very dramatic when the load factor gets beyond about 70 or 75%. And so you have a case where the number of probes increases very, very quickly. With chaining, this isn't the case. Performance degrades more slowly. Nevertheless, it does degrade. And the emphasis here is on the fastest possible performance. These are high-performance data structures, and therefore it makes no sense to have slow or unwieldy structures. So you could have a chaining strategy where the load factor exceeds 100%. This is not possible with probing. So in the case of probing, once all the array elements are loaded, once there is something in each slot, then you're full and you're done. So you cannot possibly exceed 100%. However, with chaining, you can always tack one more element on to the linked list. And so you can actually exceed 100% load factor with the chaining strategy. However, performance begins to degrade. If you have a hash table implemented with chaining where the chains have, say, 15 to 20 elements in them, then obviously the performance will begin to degrade. So we want to focus now on the chaining strategy, and this is the most important one because it's the most commonly used, and is probably the implementation that you will be required to use for your CS310 project. So with probing, the strategy is we're going to find an alternate location if there's a collision. With chaining, we're going to store it exactly where it hashes to. This is the idea of closed addressing. It goes exactly where we think it should, and it gets inserted into a linked list at that location. If most of the linked lists are very small, none contains more than maybe 5 or 6 elements, then you can maintain big O of 1 behavior. And again, the length of the linked list is actually a factor of lambda, the load factor, but it's not relevant at all to the number of elements that are in the hash table. Therefore, since the input size n, which is the number of elements in the hash table, is not related to the number of elements in any of the linked lists, we can say that it's big O of 1. The worst case behavior, which you really should never see, is the case where you have a truly dreadful hash code method and all of the elements end up in one linked list. In this case, you have big O of n behavior. So here we have the beginning of a hash table implementation. Some comments are in order. Note here that we have KV. This is key and value, and there are two parameterized types. We have the three size variables that I mentioned before. The current size, which is the number of elements in the hash table. The max size, which is the maximum number of elements that can be inserted into the hash table. And then we have the table size, which is actually the size of the array. The mod counter is used by the iterator. So here's the declaration for our array. We have an array of linked lists. Now we should comment that it makes absolutely no sense to use an ordered linked list in a hash table because it doesn't speed up operations. That is, searching an unordered linked list is big O of n. Searching an ordered linked list is also big O of n. But insertion is longer. Insertion takes longer for an ordered list. To insert an item into an ordered linked list is big O of n. To insert an item into an unordered list is big O of 1. You simply insert at either end. Therefore, using an ordered list makes no sense because it is actually slower. Notice too that your linked list class almost certainly takes type E, but now we have a KV. So we have the adapter pattern. That is, what we're going to do is go ahead and use our linked list without rewriting it. We want reusable code. We want to be able to use code that we have written and tested and know that it works. So we will use an adapter pattern. We will create a wrapper class. And so the E here is the wrapper class. So we're taking a KV and making an E out of it. Here's the example of our wrapper class. I've called this dictionary node. It looks a whole lot like the node class in your linked list, except of course there is no next pointer. Rather, what we have are two things, the key and the value. Essentially, this is a way to store two things in one cell. We could create parallel arrays, have an array of keys and an array of values, but this is not desirable for a number of reasons. Having everything in one place, that is, both the key and the value, in one place makes it easier and more manageable. Therefore, we create these dictionary node classes and store the key and value in them, so we have one item that wraps or contains these two. We also have to have a compare to method here. So notice we have dictionary node implements comparable, and what we're comparing are dictionary nodes. This is important. It's true that we're using the keys for comparisons in hash tables. However, we want to be able to compare one dictionary node to another dictionary node. And so we write the compare to method here, and this compare to method merely calls the compare to method on the key class to do the comparisons. So this allows us to compare instances of dictionary node, and it does so by using the key. Here's the constructor of our hash table. Again, we're initializing current size, max size. The mod counter is for the iterator to make it fail fast. The table size, which is the number of elements in the array, is set to max size times 1.3. Now we create our unordered linked list array. So we have an array of unordered linked lists. Also notice this loop here. It's important to understand this basic principle, and many times beginning students don't quite capture it. And so I want to use the sketchpad for a minute and talk about this because it is an important concept that goes way beyond this particular instance. So we have the declaration of an array of linked lists. This creates a single variable, and we've given it the name list. So it's actually an array. We have unordered linked list and then array brackets list, but this variable is a scalar. There is no array at this point. So then we have the declaration to make the actual array. And as you can see here, we say list equals new unordered list table size. At this point now, we have actually created our array. And because we've used the keyword new, then it is in a different location. It is on the heap. So as you know, the heap is this vast expanse of memory that's used for dynamic allocation of variables. So we now have an array here with however many elements that we need. It's important, however, to understand that at this point we don't have any linked lists. This may seem counterintuitive. We created the variable list, and we did this with the brackets when we created it, but that didn't make an array. That gave us a scalar that will hold an address. Then we say list equals new unordered linked list, and that gives us the array over here. Well, this spot has an address in memory. We're making something up. Suppose this hex address is 371B2116. Then list has this value, 371B2116. That is the address of the first element of this array. But again, we have no linked lists. What we have is an array of nulls. These don't exist until we make them. And that means we have to scan down the full length of this array and using the keyword new, create a new linked list, which means each of these cells will have the address of a linked list instance somewhere on the heap. Therefore, if you attempt to make a call on your linked list in one of the array locations, before doing this you get a null pointer exception. So list is a class level variable which is listed prior to this. Here, unordered list, and then we have the square brackets list. Now we create it, list equals new unordered list table size. So now we have an array, but that array has nothing but nulls in it. Then we have the for loop we loop through, and for each element in the list we make a new unordered list. They now exist and you can manipulate them. The general process for accessing a table element, that is for insert, delete, search, you have to get an array index. You need the index of where it is in the array. So first you call key.hashCode. That is, you're not writing a hash code method in hash table, but you call it in much the same way that you called compare to in linked list. You didn't write compare to in linked list, but you called it. Similarly here, you call the hash code method on the key, and then you mod this by the table size. And so if you use mod, that is the remainder of a division, this will map to the index in the array. So the hash code is in the key class, but then you need some private method, perhaps called getIndex, in the hash table where you call this, and then you perform the modulus by the table size. Then you call a linked list method on the appropriate array element to do the option that you need. Remember that you cannot compare a key and a dictionary node. This is a common mistake that students oftentimes make in the beginning. You have to think carefully about this. If the linked list contains dictionary nodes, then to compare to look for something, you have to pass in a dictionary node to do the search. So this is an example of contains. This returns true if the linked list has this particular element. So to perform this contains method on the linked list, you have to pass in what you're checking for or looking for. So you create a new dictionary node, and you have the key because you're searching based on the key, but you do not have a value. There is no value involved here. So you pass in null. Well, this null value is simply never used. Thus, when you compare two dictionary nodes, the key is used because that's what's in the compare to method. The null is not used, but it has to be here as a dummy value so that you can actually create the dictionary node. Another gotcha to watch out for. A search might return null, so this situation has to be handled. It's an easy mistake to make, and it seems like fairly simple code. So we have get hash code key. So this gets us the hash code passed in the key, and what that does is the operations I talked about. There is the hash code method called in the key, and then there is the modulus operation with the table size to get the actual index. So this is the index in the array that we're searching. We call the get method, the search method, and then we pass in new dictionary node, key, and null. So this is just like the contains method, except there's a return value here. It returns what it finds, the value that matches this key. However, you have to be aware that you might have an unsuccessful search. If you have an unsuccessful search, then your linked list method, this get here is the linked list method, then the linked list method will return null. So you're actually calling null.value, and you get a null pointer exception and crash. The solution to this problem is you must check the return value first. So we have dictionary node temp, and of course it makes sense. Since the linked lists have dictionary nodes, that's what they store, that's what they're going to return. So the list is going to return a dictionary node, so we call get with the key and a null value, and we get something back, and it is either a dictionary node reference or it's null. So if it's null, then we return null. If it's not null, we return the value at that location. So here's another example, a simple add method. So first we have to check to make sure that that the hash table is not full. If the hash table is full, you can't allow insertions beyond that point. So once you know that it's not full, then you have to check and see if you have a duplicate. You cannot insert duplicate keys. So we get the key, we look it up with the contains method, and if we get back null, then we know that it's a duplicate. So when we get here, we know that the table's not full and that the key is not a duplicate. Then we add a new dictionary node. We use the key and the value to do that. And so notice we have a one-line piece of code here to do the actual insertion. You must never have loops in the add, search, or delete methods in a hash table because these methods must be big O of 1. A word about hash table iterators. We have a new situation with dictionaries now because the iterators are not just a one kind of thing. We have K's and V's. Therefore, we have key iterators and value iterators. So, since we have two distinct iterators, we can't really implement the iterable interface here. And we also generally will have the requirement that the keys will come out in sorted order. This is because the hash tables do not store things in any particular order. They do, but that order actually is defined by the hash code that the key generates. But in terms of sorted or ordered, it is not. And so if you need the keys to come out in order, you're going to have to sort them. I should add then that if you insert or add method to sort to your hash table class, it should go in the iterator, not in the hash table class. That is, the sort goes where you're actually going to use it. It's important to point out the expected order that these iterators will operate with. And so the keys are going to come out in sorted order. So in this case, the keys are integers and the values are brands of cameras. So 1 is a Nikon, 2 is a Canon, 3 is a Leica. So these are the lookup values. So they're sorted on the keys, 1, 2, 3. These guys, of course, are never sorted based on their values. It would be an error to sort these. You do not want Canon first because there's no matching key. So you don't want to leave behind the keys and mess this up. Therefore, these guys are in order. They're actually in sorted order, but they're in order sorted on the keys. So this is the value in which they must come out. So if you get a key iterator and you call next, you're going to get 1, 2, 3. If you call a value iterator and call next, you're going to get Nikon, Canon, and Leica because they're going to come out in the order that corresponds to the key. This is easy, not hard. That is, this requirement that the values come out in the same order as the keys is actually easier to do than not do. Because you have dictionary nodes, the keys and the values are tied together. You sort the array based on the key. And this is easy to do because you have the compare to method in your dictionary node. So you merely sort the dictionary nodes and then take either the key or the value as needed, and they will come out in the proper order. Also, in this case, you have a lot of repeating code. That is, you need to scan through the entire hash table and copy all of the array elements, all of the elements from the linked lists rather, into an array and then sort it. These operations are going to be the same for both the key and the values. And so here you can create a superclass, maybe call it iterator helper, an abstract class, and then inherit from this class for the key and value iterators. So here's an example. Here's an actual implementation that you can look at. Notice that this class is abstract. It's abstract because the next method is not implemented. With the key iterator, you're going to want to return the K. With the value iterator, you're going to return the V. Therefore, you can't know which one you're going to return with next, but the rest of it you can implement. So we've created an array of dictionary nodes. Of course, you can't sort the hash table linked lists. You have no heuristic or no method for sorting linked lists. That wouldn't work in any case. If you were to sort the elements in your hash table, then you would break it. Because when you go to search for things and you go to a given location, if it changes because you've sorted the thing, then your hash table is broken. Therefore, the underlying data structure, the array that holds the linked lists, must be left unchanged. So what you need to do is scan through the entire table and copy elements from the linked lists into an array and then sort that array. Well, it sounds harder than it actually is. Here's the loop to do precisely that. We go for 0 to table size. In other words, we scan down the entire array. And then we have an inner for loop here, but notice this is a for each loop. This calls iterable. That is, it uses the iterable interface in your linked lists. If your linked list doesn't implement iterable, it should. It should because it makes this possible. So the way this works then is at index 0, we go to the linked list at that location. And if there is anything, it gets grabbed. And if there isn't anything, then we just loop back around and go on to 1 and then to 2 and then to 3 and then to 4. And so when we find a linked list that has elements, the iterable interface retrieves these one at a time and stores them in the array. So I want to switch over to the sketchpad for a minute again to look at this process. So here we have the array, which is our data structure. Here we have linked lists. Maybe this one's empty. This one has 2 elements, let's say, X and W. This one has one element, maybe a B. This one is empty. And this one has 3. So this will be sufficient for our example here. So let's call this P, Q, and S. All right, here's our destination array. This is the iterator array that we're going to use. So the outer for loop scans down this entire array for I equals 0, I less than table size, so it marches down this array one at a time. Then we have the inner loop, and it's a for each. For each element in this linked list, copy it. So there aren't any here, so we simply move down to the next one. Then we get the X, we get the W. All right, then we move down to the next one. We get the B. Move down to the next one. We don't do anything because it's empty. And when you call that for each loop on an empty linked list, it simply does nothing. It will not crash or cause a null pointer exception. So we move down to the next linked list, and here we have P, Q, and S. P, Q, and S. And so this is the process whereby you traverse the entire hash table, pulling out each element, or removing it, not removing it rather, but copy each element into your auxiliary array, which you then will sort. I should add that it's important to make this array current size, not table size. If you make it larger, then you'll have null elements at the end which will cause you to crash. So this array must be current size. This array, of course, is table size. It's the underlying data structure. So again, we have the abstract class. We have now loaded or filled in our auxiliary array with the dictionary nodes, and then we will need to sort this. So in the sample code here, I have an external class with sort algorithms in it. For your project, you probably won't have this, so you will need to write a sort method. If you do this, then the sort method goes inside this iterator helper class, not in hash table. Just as an aside, it seems to me that using a simple algorithm that's faster than n squared would be the appropriate thing here. So the has next and the remove, these are actually implemented here. That's why this class is abstract. We have one method that is not implemented and must be implemented in the iterators that extend it. So here we have the key iterator helper. It extends this iterator helper. It calls super, which means it calls the constructor in the parent class, the iterator helper. Then you have only one method to implement next, with just one line of code in it, which makes for a very, very easy class. And then you avoid the problems of repeating the code. Here's the value iterator helper. This does the values. Note that the array is sorted in the abstract class in the iterator helper. And so because the fact that you have the keys and the values together in the same wrapper, you again have one line of code to implement the value iterator helper. Some comments about chaining in general. Chaining is best suited for hash tables that have many insertions and deletions. There is an issue here with probing in these cases. The issue with probing becomes, how do you handle the situation where there are many insertions and deletions? This becomes a problem, and I want to look at this for just a moment. So here's really the crux of the problem. Suppose we have an array here for probing. This is the probing strategy. And this is why probing is not really suitable for cases where you have many insertions and deletions. So imagine that I have this situation. All right, I have elements stored here. Okay, now assume that I want to insert an in, and it actually hashes to this location. So we go here, and using this simple linear probing strategy, because it works the same way with quadratic probing, the issue is the same. So we go here to where the z is, and we can't store our in. And we go here, we can't store it, can't store it, can't store it, can't store it. And then after the t, we find a cell that's open and available, so here we store our in. We have now placed it in the array. So this is our heuristic. The place where it's supposed to go isn't available, so we find the next available slot and store it there. Generally, this isn't a problem, so suppose we need to search for n. Well, we go here and we see x. That's not an n. We move down, we follow the same set of rules. We find the n. Now we have found our element. Then, of course, suppose that we search for something else that maps to the same place. Let's assume that we search for a p. So this is a not found condition. There's no p in the hash table. It maps to this same location. So we go here and look, no p, no p, no p, no p, and so on. Then we get here, and this cell is actually null. Okay, if there were a p in the table, then it would have to be here, because the null tells me that nothing's been stored there. So I can stop looking. I can say the p is not in the hash table. But this brings up the issue here. Suppose I'm looking for the n, but before I look for the n, I come along and I delete the q. So the q is deleted and out of there. So I come to the x and I'm looking for n. So then I go to z, not an n. I go here, it's null. Okay, does that mean the n is not in the table? Unfortunately, no, it doesn't mean that. Well, in a situation like this, then what do you have to do for an unsuccessful search? That is, if an empty cell is not a sentinel or a marker that tells you you can quit looking, then you have to keep going. So I don't have any information here, so I move down to the R, the S, the T, and then I do find the N here. But for an unsuccessful search, you would have to go all the way to the end of the array and wrap around and come back until you get to your starting point. In other words, you would have to look at exactly n places to see whether or not the element you're searching for is in the linked list. If the table is size 1 million, then you're going to do 1,000,000 comparisons before you discover it's not there. This is obviously unacceptable. It needs to be a big O of 1 situation. All right, well, we could tell the difference here because I can have a different flag in this location. So we have states. State 1 is occupied. State 2 is used but vacant. That is to say, I used to have something in this cell here, but I no longer do. It's been deleted. And 3, unused and vacant. Unused and vacant. So if I hit a cell that's unused and vacant, then I can stop looking. But if I hit a cell that's been used and vacant, that gives me no information. I have to keep going. So if you have relatively few insertions and deletions in a table that uses probing, then you have a substantial number of cells in this category that have never been used and are vacant. But after you have many insertion and deletions, all of these disappear because they all end up being used, and we have this state. And so all of the unused, unoccupied cells become used but vacant. That is, there was something in there, but it's been deleted, and you can no longer tell if you can stop looking. So again, when I get to a cell like this, it doesn't have an element in it, but it used to. I have no idea whether I can stop or not stop. And so this is the reason why chaining is the preferred strategy for a hash table that has many insertions and deletions, because you don't have this problem with the linked list strategy. It's important that whatever strategy you do use, the add, search, and delete methods must not have any kind of loop. These methods must be big O of 1. Performance is paramount. Reverse lookups are always bad because hash tables are stored based on the keys, not the values. When you have a reverse lookup that is given a value, find the key. This is going to be big O of 1, but it should not be worse. Now the strategy you want in this case is to use the code that we put in the iterator to load the auxiliary array. That is that mechanism for traversing the hash table. You want to use that same mechanism, but you should not use iterators in order to do reverse lookups because the cost is too great. In the best and average cases, chaining is slower than probing because of the overhead associated with linked lists. However, when we say slower, we don't mean complexity. We say slower, we mean empirical or wall clock time. Performance degrades slowly with hash tables that use chaining as the load factor increases. You could never exceed 100% load factor with probing, but you can with chaining. It's not a good idea, but it is possible. And finally, in every case, table size should be made larger than the max size by about 30%. We're going to waste space to enhance performance. It's a fair trade-off. So this concludes our lecture on hash tables.